And it turns out this EX bar is the same in both of these systems, but the B bar is 1/2 in system 2, and it's 1 in system 1. So you see that, you say, I cannot compare the probability of error. In other words, the minimum distance, even though it's greater, not allowed to do that. So we caught it. Now you see here, this system is really using more power because it's got more dimensions, but the EX bar works out to be the same, but I caught it on a B bar. Okay, I'm going to get it on one or the other, okay, this way. So you only need to look at the EX bar, the B bar, if you're going to compare the probability of error. This will guarantee you always get a fair comparison. Okay. And now, of course, you can fix the PE bar and look at the amount of energy per dimension if the B bar is the same, or you could fix the energy per dimension and the probability of error and then look at the bits per dimension being transmitted. If that's greater, then that's a better system. So these are fair comparisons. So I have a section in the notes on that. It is an important area. I think what often happens is that this will be easy for you in a class. You'll be able to look at those two things and compare systems and say, okay, you know, Cioffi told us, look at these 2 and 3. You'll get the answer correct. What happens is people get out and start working, kind of forget their roots, and it's real easy to make a mistake forgetting that one system or another is somehow using system resource unfairly with respect to a first system, and then come up with a bad comparison or some kind of result. So I guarantee you, if you stay with that, even if you get caught up in some kind of competition, which typically happens in transmission, 2 companies fighting over a different way to do something for some kind of transmission standard, this is a fair way to make comparisons. So my third topic for today here in the last 10 minutes, what I'd like to try to get into is different types of modulations. We know how to compare them now fairly, so we can actually start to talk about them formally, all of which will be for the additive white Gaussian noise channel. Now this first one is one that is a very old modulation type. You don't see it too much, but it goes by the general name of binary orthogonal. Often very cheap to implement the detector for systems that are binary orthogonal. And they have n equal to 2 and m also equal to 2 messages. So B is equal to 1. And the signal constellation looks like this. We have 2 basis functions, and one of the messages is essentially transmitting the first basis function, and the other message is transmitting the second basis function. Now clearly this is square root of EX on this axis, and if we also put square root of EX on the second axis, then the average energy is EX. The minimum distance, d min, is square root of 2 EX. And the probability of error is then, since there's one nearest neighbor, Q of square root of EX over 2 sigma. We're going to stick this inside. This way we have inside the argument. I should have sigma squared actually there, because it's 2 sigma in the denominator, and then I took the square root of 2 out of the numerator, left the square root of 2 in the denominator, which is Q of, in this case, well, we'll leave it in that form. We'll take the energy, square root of 2 in the denominator, sigma squared. So that's our probability of error. Why are these systems used? Well, the receiver is usually pretty easy to implement, because essentially we go through the 2 match filters for the 2 basis functions, and all we got to do is compare the outputs after sampling. Okay, and if basis function 2 output is larger than it was this message that was transmitted. The basis function 1's match filter output is larger than basis function 1 was transmitted. So that's a pretty easy receiver. Think of this in the frequency domain. These are two bandpass filters. Okay, so that might be pretty easy to do. Send one frequency, that's a 0. Send the other frequency, that's a 1. Okay? Could be in the time domain. Okay? In which case I look in one time interval or I look in a subsequent time interval. And whichever time interval has more energy, I decide 1 or 0. Okay? Pretty easy to implement the receivers. Not a very efficient type of transmission system. Let's look at some specific examples of this that occur. The first one is called frequency shift keying, FSK. And the first basis function, phi 1 of t, we could actually write, if we had a symbol period of capital T, it's square root of 2 over t, sine of pi t over t. 0 is less than or equal to t is less than or equal to capital T and 0 everywhere else. And phi 2 of t is equal to square root of 2 over t sine of 2 pi t. So the frequency is doubled. 0 is less than or equal to t is less than or equal to capital T. That works. The demodulator, really easy. Take y of t, and we got essentially bandpass filter 0, which corresponds to that frequency, and we've got band pass filter for the 1 message, which is the second frequency, and we pick the largest. Now this is still used in pagers a bit, this type of transmission. It's used in the very, very first computer modems back in the late 1950s and early 60s to send 75 bits per second over a telephone channel. Of course, we have much faster speeds than that today, but reminding that we didn't really even have integrated circuits back then, it was pretty hard to implement receivers, so we might have some bulky stuff around just to get the bandpass filters implemented. So this is a form of it, pretty easy to do the receiver. The second form that you'll see in use is what's called return to 0. And it's essentially the same thing in the time domain. So phi 1 of t looks like this. It's 1 over square root of t out to capital T, starts at 0. And phi 2 of t is essentially a square wave over the same interval. So you can still got 1 over square root of t here. You got minus 1 over square root of t there. 0, t over 2, and t. Now clearly that's orthogonal to that. If you multiply those two together and integrate, you get 0. Okay. I call it return to 0 because it returns to the same level at the beginning of each symbol period. So really the difference occurs in the second half of the symbol period. Now, the output for this, output from the channel, is processed by essentially a low-pass filter, and that gives you the message kind of for this first basis function here, and then a bandpass filter is the second message there. So pretty easy to implement. You see it being used in a lot of digital communication systems where efficiency is not necessarily incredibly important. Pretty easy system to design. Look at low frequencies or look at this second frequency here for the square wave. Look at the difference. Now clearly this doesn't look so smart here when I do it this way. Now this is clearly the same thing as the FSK. But look over the first half of the interval. Okay. It's the same thing. Why did I do that? What am I getting by sending the same thing for half the time that I have available? There's no distinction that's being made between the signals with this type of transmission. But it is something that sometimes is used in the in early transmission systems, and in fact even what's some of the old Ethernet type things. If you still got a 10 megabit per second Ethernet system, it uses this, basically a form of this return to zero type transmission. It's since been replaced in later systems by more efficient transmission. M-area orthogonal transmission just continues the same trick. Every basis function gets a message. And it turns out the probability of error from this by the nearest neighbor function, since the number of messages is equal to the number of dimensions, the union bound is the tightest bound you can get and works out to be square root of EX over 2 sigma, because we can always draw a triangle between two closest points and work out the same minimum distance formula we got earlier. Some of the pagers actually use more than 2 frequencies. Okay, so they'll have 4 frequencies instead of 2, so there'll be 2 bits per symbol, and you could analyze the performance like this. Yes, sir? It is, I have less than or equal to here in my notes. I think it is less than or equal to. That's a very good question. There's a possibility I think you might be right. I think we could actually write it as equal to in this case also. It's certainly true for 2 points. I'm not sure if it's true for 3 or 4 or more than that, but the upper bound is in any case is safe because that's the union bound. Okay, a final form of this M-area orthogonal is what's called pulse position modulation, PPM. And so guess what this looks like is, most of you are going to guess already, phi n of t, set of basis functions that go from n minus 1 t to n times t. So you've got basically time chopped up into little blocks. And each message is determined by the position of the received energy. So that's called pulse position modulation, or PPM, for that reason. And where this is used, if you've got one of these like home plug type things that transmits data around your house, they use something called HPNA in there. And actually, this is the format that's used to transmit data from one computer to another within your house. They actually have 32 positions and 5 bits per symbol that are used in the HPNA systems for transmission. I'm not aware, other than that and the pagers that have the 4 frequencies of any other M-area orthogonal types of system. Now you can see we're throwing away a lot of bandwidth or dimensions here. We're only getting 1 message per dimension. If you actually go through fair comparisons, these systems obviously are not going to fare very well. You've got a certain amount of energy, a certain amount of dimensions to use. We're going to want to pack more points into the dimensions than just 1 point per dimension to get a good design. And in fact, that's going to lead us, when we get into the lecture on next Tuesday, into what are called PAM and QAM, which are much more efficient transmission techniques than these orthogonal methods that were used in early communications. So with that, we'll sign off for today.